So far in this video series, I've referenced this term Ethernet frame quite a bit, but we haven't really looked at what is that. In other words, I've said that when your NIC card sends out its bits, it gathers them and formats them into this thing, this structure, this protocol data unit called an Ethernet frame. And then it uses carrier sense multiple access to know when it can send the frame and if the frame has collided with anything else. But what does the frame actually look like? Well, let's take a look at them. So in the original Ethernet implementation, and then in Ethernet version 2, which is called Ethernet DIX here for Digital, Intel, and Xerox, we can see the original Ethernet frame structure up top. And then when Dr. Robert Metcalf and some of his engineering friends formed the 802 committee, and then they formed the 802.3 working group, they modified a little bit, and 802.3 looks almost the same as Ethernet, but you can see here the main change is that while Ethernet had a type code, 802.3 has a length field. So let's dig into each one of these fields here and see what do these fields represent? What are they used for? So let's start with the first field, the pre. So that stands for the preamble. So the preamble is 7 bytes of this recurring pattern called 10101010. So that's the preamble. And the purpose of the preamble is simply so that the receiving device can synchronize its clocking. In other words, the receiving device will know exactly when to scan the wire, probe the wire to make sure it picks up a 1, picks up a 0. Because remember, the way Ethernet works is that I'm going to hold my voltage up to a certain level for a certain amount of time to represent a 1. Then I'm going to let it go. I'm going to wait, a few nanoseconds and then hold it up to a different level for a amount of time for a 0. So if I'm sending this to you, your receiving circuitry has to be monitoring that wire at the precise time to know to look when to get that voltage level, to know when to see the 1s and 0s. So the clocking has to be the same. If I'm putting the bits on the wire at this rate, you have to be sampling the bits off the wire at the same rate. So in order to ensure that, we have these 7 bytes here of the preamble. And then after that, we have one more byte called the start of frame delimiter. The start of frame delimiter. Now, what does this 5-4-3 rule have to do? This is just some sort of like historic artifact, but I thought you might find it interesting in case you ever ran across it. So in the old days of Ethernet, the 5-4-3 rule simply said this, that Ethernet, when it was developed, one of the things they had to determine was when I put a bit on the wire, a 1 or a 0, how far do I want it to go? Because think about how this is actually happening at the physical layer. It's like I'm putting some electrical energy on the wire, and my rules state it has to be a certain level held at a certain amount of time so that you can recognize it as a 1 or a 0. Here's the thing with electrical energy, though. If you put electrical energy on the wire, the farther and farther it gets away from the source, it becomes what's called attenuated. Attenuated means that electrical energy gets more and more dissipated, less and less what it looked like at the beginning. So if I put a nice solid wave on the wire, I'm holding it at a nice solid consistency for a certain amount of time, then I let it go, that wave gets sort of distorted the further and further you go away from the source. That's called attenuation. So if I have two things that are really close to each other, there's not much attenuation there. So I don't have to use a whole lot of electrical energy. I don't have to use a big massive battery or a big electrical source to put energy on that wire because the receiving device is so close to me that the electrical energy won't change much between point A and point B. But if point A and point B are really far apart, and I know that that electrical energy is going to dissipate by the time it gets to point B, I have to think to myself, okay, well, if they're going to be really far apart, that means the electrical energy at the beginning has to be really strong so that by the time it gets here, even though it's gotten weaker, it's still strong enough for point B to be able to receive it and to be able to tell that it's a 1 or a 0. So it's a trade-off, it's a balance. So the designers of Ethernet said, well, we could make it to where we support really long cables of like a mile or 2 miles, but our electrical source is going to have to be huge, huge electrical battery or lots of voltage so that it goes that far. Or we could take the opposite approach. We could design this as a technology of, well, it's really only meant to connect two devices sitting on a table that are like 2 feet apart from each other. That way we won't have to use very much electrical energy. So they decided that based on certain Ethernet standards, the cables would be certain lengths. So we'll actually see that coming up right here in just a moment. So what does that have to do with the 543 rule? So let's take the original implementation of Ethernet. The original implementation of Ethernet specified that a single cable, due to electrical attenuation and everything, could be no more than about 185 meters end to end, which is actually pretty long. But what if you had a really large company, like a skyscraper of 20 or 30 stories? One cable of 185 meters wouldn't cut it. You needed something longer than that. So that's when they invented Ethernet hubs or Ethernet repeaters, where you could repeat the signal. The idea with the repeater was, okay, when the signal comes in, strengthen it, refresh it, and then send it out on another 185 meters of cable, potentially. Well, here's the problem, though, is that imagine I have all these cables with repeater, repeater, repeater. The way the repeater works is that the repeater, just like the NIC card on your laptop or PC, is listening to that cable. And it's listening for this preamble. And the first 5 to maybe 6 bits of the preamble are sort of like ignored while the repeater says, okay, I think that's something. Yes, okay, that's a 1 and a 0. So by the time the repeater says, yeah, I got it, that's a 1 and a 0 coming in. The first 5 or 6 bits of that preamble have been what they call consumed. They've sort of been dropped off. And so now when the repeater is taking that frame and copying it and repeating it, it can only copy and repeat what it could recognize. So if it wasn't able to recognize those first 5 or 6 bits at the front end, it can't copy and repeat them. So now you've got a frame that came in, and now the one that's being repeated is a tiny little bit shorter because the first 5 or 6 bits of the preamble were sort of wiped out. It couldn't really see those. Now, if I've got lots of repeaters, one after the other, what does that mean? That means that preamble is getting shorter and shorter and shorter and shorter, and you run the risk that by the time that Ethernet frame gets to the destination, the preamble might not be long enough for the destination to lock onto it and be able to actually start sampling that frame. It might miss the frame entirely because there weren't enough preamble bits left, because all this long string of repeaters consume them one after the other. So the 543 rule was designed to solve that problem. They said, okay, here's what we're going to do. Our rule is going to state that you can have a maximum of 5 segments. That's it. No more than 5 segments end to end, and then you're done. Those 5 segments can be connected by no more than 4 repeaters or 4 hubs. And only 3 of those 5 segments can actually have hosts on them. 2 of them should just be used for transport. Repeater to repeater, nothing in the middle. 3 of them can have hosts connected to it. So that was the 543 rule, and it was all designed to avoid the situation of what I just described. But that was with coaxial cable that was only 185 meters. With today's Ethernet, that's not so much of a big deal anymore. But just in case you ever came across that term, the 543 rule, I want you to know what it was talking about. Okay, so that's the preamble and the start of frame delimiter. The next field, actually the next 2 fields, go into something called the addressing fields, which is what's called a MAC address. So Dr. Metcalf and his friends, when they were designing the Ethernet frame, they said, okay, this is going to be a technology where there's multiple devices tapped into a wire. Remember, the original Ethernet was this big, long coaxial cable stretching down a hallway, going up and down through floors, and all these Alto Xerox PCs were physically tapped into it. So the idea was, okay, if I have multiple devices on this wire, if device A wants to send something to device B needs to have an address. We need to have some way of saying, hey, this frame is for you. All the other devices on the wire that are also going to see the electrical energy, it's not for you. Ignore it. It's for PCB. So they said, okay, that is a media access control address. In other words, how do we access the media? Media access control address, a MAC address. So the MAC address they decided was going to be 48 bits long, so 48 bits end to end. And while laptops and PCs and everything see that as a binary number, of course we as human beings can't deal with binary, so we have to translate that into something we can use. And so we see that represented as hexadecimal numbers. Now in the event that you have never worked with hexadecimal before, let's just do a quick tutorial on that. And if you're already familiar with hexadecimal, you can fast forward the video past this section. So to explain hexadecimal, I briefly want to go back to something that you already know, which is decimal. So any number is divided up by placeholders, right? If I have a 3-digit number, that means I've got a placeholder for 3 digits. And the value of those digits depends on the value of the placeholder. So for example, this right here, this placeholder, if we're talking about decimal, is the ones position. I can put any number from 0 to 9 there, and that is the ones position. So I could put the number, for example, 7, and that means 7 times 1. Now if we're talking decimal, which is base 10, that means every subsequent placeholder is a multiplier of 10. So we take the previous one, multiply it by 10, that gives us the tens position. So if I put another 7 here, that means 7 times 10 instead of 7 times 1. And then we multiply that by 10 again, and we get the hundreds. So now we've got 700 plus 70 plus 7, 777. So that's decimal. Now if we're talking about hexadecimal, we still have placeholders, but hexadecimal is a base 16 counting system. Base 16. So the first placeholder is still the ones position. That doesn't change. But here's what's different. In a base 10 system, each placeholder could have a single digit ranging from 0 to 9. Right? There were 10 different combinations that could be placed in each one of these digits, in each one of these placeholders. Well, in hexadecimal, each placeholder could have a single digit ranging from 0 to F. You say, F? What's that? Well, in hexadecimal, you still start out with your decimal digits, 0 through 9. That only gives us 10 digits, and this is a base 16. We need 16 things, 16 digits. So now we start going into letters, A, B, C, D, E, and F. So in hexadecimal, A would be the equivalent of 10 in decimal. B would be the equivalent of 11. C would be the equivalent of 12, and if we keep going on up, F is the equivalent of 15. So in a single placeholder here, I could have from 0 to F. So if I put, let's say, A right here, well, we know that's A times 1. Well, A is really the number 10 in decimal, so that's 10 times 1, that's 10. If I put, let's say, 3 right here, well, in decimal, we multiplied by 10. Each placeholder was a multiple of 10 from the previous placeholder. Well, in hexadecimal, we're talking about base 16. So we multiply by 16. So we got 1 times 16, which is the 16's position. The next position is going to be 16 times 16, which is the 256's. So 3A in hexadecimal is 3 times 16, which is 48, plus 10, plus A times 1, which is 10. So 48 plus 10, this is 58. So the hexadecimal number, hexadecimals are usually represented as 0x, but not always. So 0x3A in hexadecimal is equal to 58 in decimal. If I put a 2 right here, that'd be 256 times 2 plus 16 times 3 plus 10 times 1. So why did they do it this way? Well, when it comes to MAC addresses, I'm not going to do all of it, but what have we got here? We've got 1, 2, 3, 4, 5, 6, 7, 8. So right now, 8 times 4, so this is 32 bits right now out of my 48. So if this was the first 32 bits of my 48-bit MAC address and I want to represent this in some way that was meaningful, they decided to use hexadecimal. So they said every 4 bits is going to be represented by a hexadecimal character. So that number right there, 0010 in binary, if that were a decimal number, that'd be the number 2. Well, we know that in hexadecimal, 2 is the same. It's still 2. In binary, 1111, what is that in decimal? Wasn't that the number 15? 8 plus 4 plus 2 plus 1 is 15. But in hexadecimal, 15 is F. This here's the number 1. This here's the number 13. So that'll be D. So your MAC addresses are always going to be represented like this. The 48 bits in binary are going to be showing up to you in whatever show command you use as a hexadecimal number. So for example, here's an example of a MAC address, AAAA.AAAA, so on and so forth. Now depending on the device you're on, they will sometimes display MAC addresses differently. Some devices will show MAC addresses like this. For every 4 characters, hex characters, it'll be separated by a dot. Sometimes that same thing will be separated by colons. Sometimes every 2 will be separated by colons. It just depends on the device that you're on. The main thing is that these are hexadecimal characters and they add up to a total of 48 bits in binary. So of our MAC address, the first half of it, the first 24 bits, is what's called an organizationally unique identifier. What's that mean? Let's say, for example, that I had a machine shop in my garage, and I thought, you know what? I have all the equipment necessary to create my own Ethernet adapters. I want to start making my own Ethernet adapters and sell them on the open market and compete against Intel and some of these other big companies. Well, in order to do that, all of the adapters that I create in my garage, in my machine shop, the first half of them have to have an organizationally unique identifier that is unique to my organization. So what would I do? Well, I would go to the IEEE and I'd pay them something like $500 American dollars or something like that. And once I pay them some money, they will give me an OUI. And now every single NIC card that I create in my machine shop will have my OUI at the front half. They will all have the same number. And then the second half of the address, as you can see here, will be unique. So every single NIC card should have its own unique MAC address burned into it at the time of manufacture that is unchanging. So the manufacturer's stamp, the OUI, will be the first half, and then the second half will be a unique number just for that MAC address, just for that NIC card. And you can see here, if you're curious, I have up here, you can go to this website, wireshark.org/tools/OUI lookup. Let me go ahead and make this a little bit bigger here so you can see it. There is the URL. And what's kind of nice about this is you can type in OUIs to see who owns those OUIs. For example, look at this one right here. 0000.0C. Who owns that? Search. Cisco. Cisco owns that one. You can type in, you can look at the OUI of your own NIC card on your laptop or your PC. Maybe you own 0002.11. Does anybody own that? Nature Worldwide Technology Corporation. So this is kind of and there are other websites that do the same type of thing where you can plug in an OUI and it will tell you what company owns that OUI. But we're not done with the MAC address just yet. So the MAC address here, we know that this is the first 24 bits, first 3 bytes. Let me go back to the whiteboard here for a moment. So let's say this was my MAC address. This is the first 32 bits of my MAC address. Let me get rid of some of this. Well, the first byte is this. That's the first byte, the first 8 bits. In every MAC address, in the first byte, this least significant bit right here, I'll put a little box around that, that bit has a special meaning. That is called the individual / group bit. If that bit is a 0, that means this MAC address belongs to an individual device. This is a unique MAC address that doesn't belong to anybody else. Clearly, this one is not a 0. If it's a 1, that means this MAC address is a group address. You might be wondering, what do you mean by a group address? Well, think of the concept of a broadcast. What is a broadcast? A broadcast is I put one data unit on the wire and it's meant for everybody to see. Well, if I'm going to put that data unit into an Ethernet frame, the destination MAC address of that frame has to indicate this is not for anybody in particular, this is for everybody. Well, the broadcast MAC address looks like this. Or in binary, it's just 48 bits of all ones. That is the broadcast MAC address. And you can see here that if we actually convert that into binary, which I did, and I take a look at the first byte, 1, 2, 3, 4, 1, 2, 3, 4, I think I've got all 4 of them there. We can see here that the individual group bit is set to a 1 because that is a group address. If you have any experience with multicasts, at layer 2, there are special MAC addresses for multicast. Those are also group addresses. So their least significant bit will also be turned on as a 1. So any MAC address that has a 1 bit here means it does not belong to a specific NIC card. It belongs to a group of devices. That is the individual group bit. Now, in addition to that, the bit right next to it, right here, that bit also has a special significance. That's called the universal or global local bit. If that is a 0, that means this address is universally / globally unique. That means nobody else in the entire world should have that MAC address. It belongs to you. It is yours. Now, if I was to go into a device and change its MAC address, which you actually can do on most devices, there's nothing that forces me to do this, but if I'm changing my MAC address, what certainty do I have that the new MAC address I'm putting on there manually isn't already out there in the world somewhere that's reserved for somebody else? I don't know. So if I change it, I should take that second bit and flip it to a 1, which means that I have now created what's called a locally administered address. I mean, this MAC address is not the MAC address that was burned on here from the manufacturer. It has been locally modified. No guarantees anymore that this MAC address is unique. So those 2 bits have special meaning there. And that's what this slide is referring to. All right, so within the Ethernet frame, Ethernet version 2, after our MAC addresses, after we have a destination MAC and a source MAC, we have a type field, 2 bytes long, and this indicates what type of upper layer data is this carrying. Some common type codes you might see. I'll just say them verbally here to you. Actually, let's see here. Do I have a way of doing this? No, not let me do it. Okay. Okay, so if the type code you see is, actually I want to go ahead and type this out. Here's some common ether types. These are probably the three most common ones that you'll ever see. 0x800, that means this Ethernet frame is carrying an IP version 4 packet. 0x806 means it's carrying an ARP, either an ARP request or an ARP response. And 0x86DD means we're carrying an IPv6 packet. There are many, many other ones as well. And if you're curious about those, you can go to this website right here. I'll go ahead and make this a little bit larger so you can see it. cavebear.com, archive cavebear ethernet/type. You can pause this video for a moment if you want to write that down. There are other websites that do this as well. You can just Google Ethernet type value or type code. And from here you can see all the different type values and what they've been assigned to. Now with the 802.3 frame, they decided to change that into a length field. And the length field, as it says how long is this yellow portion here, our 802.2 header and our data. So I'm going to talk a little bit more about this when we get into the section about the size of Ethernet frames and what are meant by runts and giants and things like that. But for now, the Ethernet specification says that an Ethernet frame, that the data of an Ethernet frame should be a minimum of 46 bytes in size up to a maximum of 1500 bytes in size, 46 to 1500. That being the case, sometimes the question arises, okay, well, after my source address, how does the NIC card that's receiving this frame know if the next 2 bytes are a type value or a length value? How does it know? Well, here's how it knows. All of the valid type codes are values that in decimal are greater than or equal to 1536. You might say 1536, what about 1501? Well, actually the values of 1501 through 1535 are undefined. They are sort of left there for future use. But the type values of 1536 and above are used for ARP and IPv4 and IPv6 and all those things in that list that I just showed you. So clearly if my type code is some number that's like 1600 or 3000 or something, that could not be a length field because the length field will never be greater than 1500 because 1500 is the maximum size of the frame. Now, if we're talking about 802.3, you might have been thinking, well, if we didn't have a type field, how does the receiving device know what the data is? If it should go to the IPv4 process or the IPv6 process, or if it should go to ARP. Well, this is where the 802.2 working group came into play. Remember, 802.2 was the working group that came up with the logical link control, that upper sublayer of the data link layer. And they said, okay, we're going to put 3 subfields in here. These 3 subfields comprise your logical link control. DSAP stands for Destination Service Access Point. Destination Service Access Point. It's basically the exact same thing as a type code. It's a value, and there's certain DSAP values for IPv4, IPv6, and all sorts of other stuff too. SSAP, as you can probably guess, is Source Service Access Point. Usually these two values are the same. Whatever the protocol number was that created this field at the source is going to be talking to the exact same protocol at the destination. It's not always the same, but the vast majority of time, these two numbers are the same. The control field. In modern day implementations of Ethernet, the control field really isn't used for anything. But what this is for is because remember, LLC, the 802.2 working group, didn't create LLC just for Ethernet. They said, we want lots of different types of layer 2 protocols to make use of LLC. So they said, okay, well, we want LLC to be used in some protocols that at layer 2 are connection oriented. So for example, LLC designs basically what's called 3 different types of services. There's what's called unacknowledged connectionless mode, That's like Ethernet, right? When you send out an Ethernet frame, do you get an acknowledgement back for it? No, you don't. So Ethernet is unacknowledged, it's connectionless, right? When you send out an Ethernet frame, do you verify first that the destination actually exists before you send it? No, you don't. So Ethernet is unacknowledged connectionless mode, which means the control field really doesn't do anything. But if you're using another type of layer 2 protocol, off the top of my head, I can't think of what they would be, maybe some like mainframe, IBM, SNA type protocols, you might have connection mode, which means you actually establish a connection first, you get acknowledgments back, sort of like TCP at the transport layer. And there's a third mode called acknowledged connectionless mode, where you actually do get acknowledgments back even though you're connectionless. I don't know what layer 2 protocols actually use that. So if you're using one of those other types of layer 2 protocols, which I don't know what they are, that are either doing connection mode or acknowledged connectionless mode, that's when the control field would actually take on significance. But in the world of Ethernet, it doesn't really mean anything, doesn't do anything. And at the end, we have a trailer, which consists of our frame check sequence. So this is used for error detection, not error correction. So the FCS field, so if you receive an Ethernet frame, by looking at the FCS field, you can tell if any of the bits in that frame have been modified or changed. But you can't tell which bits have been modified or changed. All you know is that the frame does not look the same as when the source sent it. So basically the way this works is that when the originator, the source of the frame, put this frame together, it runs a cyclic redundancy check, a CRC, which is a special algorithm where it takes all the bits, starting with the destination address, all the way through to the end of the data. So from the DA all the way to the end of the data, it takes all those bits, runs them through an algorithm called a cyclic redundancy check, which then computes some sort of number, like let's say A123. And it puts that number into the FCS. So the idea is, when I send you this frame, you're going to take the exact same bits from the destination address to the end of the data, and you're going to run it through the exact same cyclic redundancy check. And you're going to compare the number that you came up with the number that's in the FCS here. Now, if you come up with A123 and it matches this, you say, great, clearly none of these bits have been modified, because if they did, your cyclic redundancy check would not come up with the same number. And if that happened, that would be considered an FCS or a CRC error, and you would just simply throw away the frame. There's no way to figure out what changed. All you know is that that frame is no longer reliable. Something has been modified. There has been an error. So that concludes this section on the various fields and components of the Ethernet frame. In the next section, we're going to look at Ethernet frame sizes and talk about things like runts, giants, and jumbo frames.